Designing, building and controlling robots are traditional engineering tasks, but we're now seeing that engineering fuse with modern AI. I'm Dr. Charles Fox. I'm a senior lecturer in computer science at the University of Lincoln, and I specialise in robotics and AI. Join me as I discuss how large language models such as ChatGPT are evolving into multimodal models and into robotic agentic AI models. Robots are physical agents. They process sequences of multimodal data, including video and audio, but also motor control and feedback systems from their own bodies. Designing, building and controlling robots are traditional engineering tasks, but we're now seeing these engineering skills fuse with modern AI. Large language models such as ChatGPT have been performing excellently at understanding and generating text, but more recently they have evolved into multimodal models which understand and generate images, audio, video and general time series data. Robotic foundation models are large multimodal models which extend this idea to include the generation of plans and control signals for the robot itself. This forms new research and industrial areas where computer scientists and engineers need to work together to blend robotics and AI. Traditional engineering robotics includes two broad classes of robot. There are animal-like robots which can move their bases around, and there are plant-like robots which have a fixed base, such as robot arms and manipulators. They're both programmed traditionally using two components. There's a top-down planner which creates the overall high-level plan for what the robot is going to do, and secondly there is a low-level controller. The controller monitors what the robot is actually doing through feedback signals. It compares it with the plan and it controls the robot to actually execute the plan. And that's where we see traditional engineering skills such as kinematics, inverse kinematics, dynamics, inverse dynamics and control theory. Now, both plans and controls can be viewed as sequences or time series. And large language models like ChatGPT are models of languages and sequences. That means we can now take models like ChatGPT, but we can repurpose them for planning and controlling robotics. Large language models are forms of the machine learning style of AI. And machine learning is based on calculus, as invented by Isaac Newton here in Lincolnshire during the 1665 Great Plague lockdown. Isaac Newton was sent home to do remote working during the pandemic of his time. He was freed from all the administration and the politics of his university, and he could really concentrate on inventing his great theory. And we're very lucky here at the University of Lincoln to have our building named after him, the Isaac Newton building. And we're lucky to have direct descendants of his apple tree growing right outside it. That's the apple tree which supposedly launched an apple onto his head and encouraged him to invent the theory of gravity. Building on calculus, in the 19th century, statisticians developed regression and nonlinear regression in particular. Regression is a statistical technique where we take labeled training data. This consists of pairs of inputs and outputs, and we pipe the input data through a parametric function. We adjust the parameters of the function to try and make the output look as much like the training output as possible. This is very much like adjusting the parameters on a musical instrument, such as a guitar amplifier or a musical synthesizer, where we can adjust the dials to try and make the sound like the sound in our head. That's the target sound or the training sound. In general, doing this in nonlinear regression is computationally hard. In the 1960s, it was discovered that a certain form of nonlinear regression could be computed highly efficiently and in parallel using an algorithm now known as backpropagation. This means we restrict the available nonlinear functions to a particular subset known as linear in the parameters, and if we do that, our computation will be distributable amongst many small individual computational nodes, which have become known as neurons and which behave somewhat similarly to the neurons in a human brain. Backpropagation was invented by some combination of the researchers Kelly, Ivanenko, Linenmaur and Werbos in the 1960s, but remained mostly a theoretical curiosity because we lacked the computation power to actually run it at scale. It was only in the 2010s that compute power finally became available. This happened due to the rise of the GPU, or graphical processing unit. GPUs were originally designed and manufactured for use by video gamers, specifically for 3D video games. In 3D video games, objects are represented by 3D coordinates. Those coordinates have to be moved around, shifted, transposed and projected into 2D for display on the screen. And those operations are done using matrices and vectors. It turns out those are the same operations that are needed to make backpropagation go fast. And so all the technological advancements that were focused on the video games industry could then be repurposed for machine learning. And when we run these algorithms on a GPU, the result is now known as deep learning. We've recently seen the rise of the open source system PyTorch, which can be used to express algorithms and neural networks in a general purpose language, Python, and then to automatically compile and run them on whatever particular GPU or parallel system you have available. Deep learning methods were extended in the early 2020s into structures now known as transformers. Transformers are a particular class of neural network. They link up the neurons in a particular structure or architecture. These are the models that are enabling large language models like ChatGPT. The transformer architecture consists of three main components called embedding, position encoding, and attention. Embedding means positioning concepts in space. If you go to a supermarket, you will find products laid out in physical three-dimensional space. They're not laid out randomly, they're laid out so that neighboring products are related to one another. Relation in a supermarket can mean complements or substitutes. Complements means you've bought some bacon, so you might buy some eggs to go with it. Substitute means you could have bought bacon or you might replace the bacon with sausages. So both complements and substitutes can be localized together. Now, imagine a dictionary of the English language. Imagine taking each word from that dictionary and positioning that word in three-dimensional space, just like in the supermarket. This means if you visit part of that space, you will find your word, but you'll find neighboring words are connected. And underlying those words are the concepts which are connected. If we do this at scale, we can build a map of a language such as English. We're going to use many more than 3 dimensions, maybe several hundred dimensions. And this is actually a very old idea in machine learning, predating deep learning. It's previously been known as self-organizing maps or topographic maps or conceptual spaces, Kohonen networks, latent semantic analysis. Nowadays it may be known as word-to-vec, which means converting a word into a vector in the space. So word-to-vec is a form of embedding. Embedding means placing words or concepts into a space. That's the first part of the transformer architecture. The second part of the process is called position encoding. And we use position encoding to modify those vectors to show where the word or concept is. If you type a series of words into ChatGPT, known as a prompt, each of those words has a position in time or space. Some words are further away from the current part of the discussion than others. And that position is what we encode through position encoding. We do this by shifting each of the vectors. So in the supermarket example, we take each product or each word and we'll move them around a little bit to represent where they occur in our prompt. The third part of the transformer architecture is the best known. It is known as the attention mechanism. Attention means that some words are more important than others for performing particular tasks. There are certain keywords that could have been said many sentences ago, which are really important, which have to be picked up and attended to create your next prediction, whereas other words are less important and can be ignored. And to create attention, we're actually going to form 3 of these embeddings. We're going to project each word into 3 locations in the space, called the value, the key, and the query. The value is what the word actually represents and what it's going to contribute to predicting the next word being generated. The query is how the word appears as a question. If the word appears in the prompt that you've typed into a chatbot, the query is specifying what the word wants to see, what it would like to look up, and the key is the inverse of the query. The key tags each word with what kind of queries can I be used for answering. So the value is a little bit like actual breakfast cereal in the supermarket. The key is like the label on the packet in the supermarket, and the query is like your shopping list. It's a list of all the things you might have bought already, and together those queries suggest which keys you're going to look up next, and those keys then provide the actual content that you go and buy. So transformers have given rise to the chatbot architecture or large language models that we see today in systems like ChatGPT. And more formally, these are known as generative pre-trained transformers. That's what GPT stands for. So that's the transformer architecture. Generative means we're going to use the transformer to generate output. And typically that means we're going to enter a prompt as text, and in response to the prompt, the system is going to generate one word or token at a time. Pre-training refers to the idea that we make a single large model and we train it very heavily with lots and lots of data. And this is the part of the process that is very expensive and can only be done by large organizations with lots of GPU power. But the point of pre-training is that you only have to do it once. You have a pre-trained model, and given that pre-trained model, you can then adjust it or adapt it in a process called fine-tuning. And most of the work has already been done by whoever trained the model. Your fine-tuning is going to change it just a little bit to make the model do the kinds of tasks that you would like it to do. In particular, we have seen instruction tuning as a form of fine-tuning. Instruction tuning is where we give actions to the model. We might say we would like you to answer this type of question, or we'd like you to perform this type of task. Translation is a type of task, or rephrasing or rewording text is a type of task. We can create special training data sets, including those instructions, and do the fine-tuning process on top of a pre-trained model to create a custom model just for that new kind of task. Going beyond natural language, we can also train large models on other kinds of data, such as visual images. And this is giving rise to the image generation systems that you might be familiar with, such as Stable Diffusion and Midjourney. To do this, we can use pretty much the same model as for natural language. We have to come up with the analog to a word, known as a token in general. Typically, we're going to do this by splitting an image into small windows, maybe squares of a few pixels each, and we're going to consider the content of those windows as if they were words in a language, in a dictionary. We're going to create a set of all those different visual words. We're going to form a dictionary of them, and we're going to do the same embedding trick that we did with natural language. We're going to create this space like a supermarket where similar visual words are co-located together. We can do the same position encoding trick because the words are physically located at positions in an image. Each of those can be given a positional encoding. And we now have the same kind of data representation that can be fed into the attention mechanism of the transformer. So as with natural language, we can then use these transformers both for recognition and for generation. Recently, generation has got all the publicity and hype. Half the world has been happily generating pictures of astronauts on horses. Perhaps more usefully, beneath that, we've seen visual recognition progress at a very rapid rate. These are systems that can take an image of an astronaut on a horse and tell you in English text what it is, translating the image into text. When we generate images, we're not able to generate one pixel at a time as we would do for language. We tend to generate the whole image together, and we do that through a process called diffusion. That means creating an initial random collection of pixels and then progressively regenerating them to become more and more like whatever it is we have been asked to generate. We can also build large models of audio. That includes both speech and music. We can do exactly the same tricks as for natural language and for images. That means we're going to tokenize audio signals. We're going to cut the audio into small windows, maybe of a few milliseconds each. We're going to treat the content of those windows as words in a language, in a dictionary. We're going to embed them again. We're going to position encode them again. And we're going to feed them into an attention mechanism. As with vision and natural language, we can then use that model both for recognition and generation. Recognition in this context could include speech recognition. It could include music recognition and understanding. That could help you to classify the music in your music collection by genre, or it could help to recognize pieces of music when they're being broadcast so that the people who wrote the music can be paid correctly. Or it could involve transcribing the music and creating a score notation from a classical music recording. Or we can flip the models around and again use them for generation. That can include speech synthesis, including the musicality now of speech, known as prosody, but also including music synthesis, generating new compositions using the transformer models. Text, video, and audio are all special cases of time series data. And time series data more generally can include pretty much anything. It could include temporal data about supply and demand in energy generation networks. It could include stock prices. It could include signals monitoring the health of your engine. And time series analysis is a well-established statistical subfield. We can, however, apply these large language model style approaches to general time series modeling and prediction. We can do that using the same methods as before. We take whatever time series data you have, such as a stock price. We're going to cut it into small slices, like we did with the audio data. We're going to use each of those data windows as a word in a language, in a dictionary. We're going to embed it, we're going to position encode it, and we're going to feed it through the attention mechanism. And we're seeing these new machine learning style methods now outperforming classical time series statistics in many of those problem domains. As with the other models, we can flip them both for recognition and generation. In recognition, we might want to monitor energy consumption in an energy grid and try to understand what is going on, try to recognize the factors or events that are giving rise to supply and demand. We might want to classify particular types of energy usage, or we might want to classify different types of stock price motions or different types of engine failures. Then we can flip the models around and use them in generative mode. Generation can include predicting time series data, such as predicting energy consumption levels or stock prices. Sometimes we want to predict the future, other times we want to predict the past. Sometimes data has gone missing. We might have been recording a piece of musical audio and we missed a bit.
And we'd like to fill in that missing part using a generative model.
It's these time series models that bring us to robotics. Robots are physical agents. They operate in real time and they process time series data. There's sensor data coming in through their cameras, through their audio sensors, but there's also data to do with the robot's own body. These include the control signals that it sends out and the feedback systems telling us where the body parts actually are. And we can view all of these modalities as time series and use them within these large time series models. Doing this well is going to involve understanding the basic mechanical engineering. It's still going to require an understanding of the kinematics and the dynamics and the control theory so that we don't have to completely reinvent the wheel. We'd like to leverage that existing knowledge but extend it with AI to gain even more accurate planning and control. So we're now seeing the development of what have become known as robotic foundation models. These are extending multimodal foundation models now to include the robot's own actions, its motions, and its feedback systems. We're seeing these models used both for recognition and generation. We're seeing robot foundation models that are able to both recognize and describe objects and events and sounds, but also to generate plans and control signals for their own actions, and for all these modalities to interact. For example, a robot can now have a conversation with a human in a language like English, discussing what it's going to do. It can create a plan. There are methods called chain of thought, which generate series of actions. We can check that the plan is actually likely to work, and then we can try and translate that plan into a feedback control system to actually execute it as a sequence of robotic motions. For example, in current research systems, we are seeing robots with arms, which might be static mounted like a plant, or mounted on a mobile vehicle or a humanoid like an animal. We're seeing these systems recognizing and answering human questions about objects, following English instructions to create complex plans and move objects between locations using control. These research systems are making progress in domestic tasks that we would really all like to automate. Tasks like preparing meals, loading the dishwasher, ironing and folding clothes. Also working in industrial environments, especially with random natural objects like food preparation. The world has now got used to AI text chatbots and AI image generators. But as more powerful computers continue to become available, we might see robotic foundation models continue to grow, and these capabilities continue to extend and improve towards general purpose robotics and AI. If you're interested in learning more about robotics and AI, come and study MSc Robotics and AI at the University of Lincoln.